Okay, let's talk about electric fields. We saw in the last video that if you have two charged particles, say a plus Q1 and a plus Q2, that there's a force between these charged particles, force of 1 on 2, and that force is located at the location of Q2. F12 is there. Of course, there's an F21 that's equal and opposite that force. And these forces are described by Coulomb's law, K Q1 Q2 over R12 squared in the R12 hat direction. So, and this is true for any summation of charges. Let's say that we put a Q3 in here, okay? Well, if we have Q3, and let's just say that it happens to be a plus charge as well, now I'd have an F23, the force of charge 3 on charge 2. And if I want the total force on charge 2, we could just call that F2. It would be F12 plus F32, and I would get that by doing K Q1 Q2 over R12 squared plus K Q2 Q3 over R23 squared, or R32 squared. The magnitudes of those things are the same. Of course, what I missed here was the vector addition. I do need to include those vector directions, R12 hat and R32 hat. Okay, but there's a common thread in all of these terms, and if I put in more, charge 4, charge 5, whatever, there's going to be more and more. The total force on charge 2 can be written as Q2 times K Q1 over R12 squared in the R12 hat direction plus K Q3 over R23 or 32 squared in the R32 hat direction. And therefore, we define this quantity right here as E2. And that is the electric field from all the other charges at the location of charge 2. Okay? And so electric field, the concept of electric field, just allows us to ask ourselves, well, what would happen if there were an arbitrary charge placed in the proximity of other charges or even charge distributions. And so the electric field concept is really best defined by taking the Coulomb force and dividing it by the charge, which is kind of what you might define it as. E is equal to F over Q. A lot of times you'll see this written as Q0 because that charge may not actually exist. It's sometimes called a test charge. If you have a collection of charges, you can compute the electric field from each one of the charges, and then that total electric field will tell you what will happen if a test charge is placed in the location of the electric field vector. So one of the things we can do with this is ask ourselves, well, what does the electric field look like from, let's say, just an isolated charge? And so let's say that I have a charge, a plus charge, we'll call it Q1, why not? And we want to compute the electric field at any arbitrary location. In other words, it doesn't have to be a charge wherever I want to compute it. Let's say I want to compute it right here above the charge. Okay? Well, what this would tell me is that the electric field from that charge will be equal to K Q1 over, and now it'll be R1 squared. When I say R1, what I mean by that, and in the R1 hat direction, that's the vector from the location of the charge to the point where I'm evaluating the charge. This would be R1 vector. Now R1 the length of that vector, remember this can be thought of as R1 magnitude in the R1 hat direction. Okay, so let's just say we have a charge situated at the origin. Okay, so we have a charge Q1 situated at the origin. Okay, and we want to know what's the electric field at this distance here, y equals, let's say, 3 meters. Okay, the charge Q1, we'll let it have a magnitude of, I don't know, 1 coulomb. Okay, a charge of 1 coulomb, and we want to know what's the electric field at y equals 3 meters. You know, so we're going to compute the electric field. We'll call this point A. Why not? The electric field at A is equal to K times Q1 over R, and you could call it, I guess you could call it 1 to A, R from 1 to A squared, the vector 1 to A. So let's do that. K, 9 times 10 to the 9 Newton meter squared per coulomb squared, times Q1, 1 coulomb, over R1A, which is 3 meters squared, in the R1A hat direction, which is plus y hat. Okay, and so I can do that math there if I had a calculator that was operational, which I don't seem to have one around me in here. Let me pull up my phone calculator. Not the best thing to use for these, but you know, sometimes you got to do what you got to do. 9 times 10 to the 9. Oops. 9 times 10 to the 9. Times 1 divided by 3 squared, which is 9. Well, this is, could have done that in my head. Alright, so notice what I'm going to get is 1 times 10 to the 9 newtons per coulomb. Okay, and in the y hat direction. Alright, so let's do another one. Let's do the same thing, but let's do it now at x equals 3. This will be point B. X equals 3 meters. The electric field at B, K Q1 over R1 to B squared, R1B hat. And that's, maybe you see this is going to be exactly the same. Everything here, it's going to be 9 times 10 to the 9 Newton meter squared per coulomb squared, times 1 coulomb divided by the same distance, 3 meters squared. The only difference is the direction. The vector from 1 to B, R1B, is in the x hat direction. And so this will be 10 to the 9 newtons per coulomb x hat. Like that. Okay? Maybe you can guess what it's going to be at point C, which is y equals 3 meters, minus 3 meters. Y equals minus 3. The electric field at C would be equal to 10 to the 9 newtons per coulomb in the negative x, or y hat, negative y hat direction, or minus 10 newtons per coulomb y hat. And if I did point D over here, where x is equal to minus 3, you guessed it, you're going to get minus 10 newtons per coulomb x hat. In fact, anything on this circle, this 3 meter radius circle, if I picked a point right here, what I'm going to get is a magnitude, let's say that, call that point E. E at point E is equal to, oh, and all these are vectors. I can put vector symbols over them. That's going to be a magnitude of 10 newtons per coulomb, 10 to the 9th newtons per coulomb. Okay? And then it's going to be a unit vector in that direction. So, I don't know, maybe that direction would be minus square root of 2 over 2 x hat plus the square root of 2 over 2 y hat. Notice that would be a unit vector if I chose this angle to be 45 degrees. How did I get that as the unit vector? This would be, in other words, R1E hat equals minus square root of 2 over 2 x hat plus square root of 2 over 2 y hat. Let's think for a minute just about how I got that, because that can be really confusing for intro students. Remember what I'm doing is I'm looking at this point right here. Whoops, not quite right. This point that's 45 degrees at a 45-degree angle, right? And I'm looking for the vector in that direction, this R1E hat. So this triangle that's formed here is, let's zoom in, it has a hypotenuse of R1E. It has an x component, let's call it just XE, and a y component YE, right? What we know is that the angle is 45 degrees. So we know that the sine of 45 would be opposite over hypotenuse, right? And we know the sine of 45 degrees is the square root of 2 over 2. We know the cosine of 45 degrees is also XE over RE, rather, adjacent over hypotenuse, right? This is in the negative x direction, and so that's also the square root of 2 over 2, because it's the cosine of 45. It's 0.707, the square root of 2 over 2. So if I'm looking at this vector R1E, it's going to be R1E magnitude times, oops, let me do it like this. Cosine, let me write it better. Rats didn't get it all. Okay, that's fine. Minus R1E cosine theta x hat plus R1E sine theta y hat. And notice what that gives you is minus R1E cosine of theta is square root of 2 over 2 x hat plus R1E, the sine of theta is the square root of 2 over 2 y hat. So what this equals is R1E times minus square root of 2 over 2 x hat minus or plus square root of 2 over 2 y hat. And therefore, this part must be R1E hat. And that's why I ended up getting R1E hat is minus square root of 2 over 2 x hat plus square root of 2 over 2 y hat. Okay. I'm concerned about this video. I hope this actually is working okay. But at any rate, what this shows you, let me redraw this down here. I'll use black again if I can. If I have an isolated positive charge at the origin, okay, and I look anywhere in equal levels around there, what I have for an electric field is 10 to the 9th, if I look in that 3-meter circle anywhere there, I have an electric field with a strength of 10 to the 9th newtons per coulomb. And so what that looks like is an electric field that is radially outward away from the positive charge. Okay? You might be able to surmise that if we had a negative charge here, I get exactly the same thing, except those vectors are all directed inward. And so the electric field from a negative charge looks like it's pointing inward. And you say, well, okay, that's all for a 3-meter radius circle. What if your circle is wider than that? In other words, what if I had, let's say, a 6-meter radius circle? Well, how does that change things? Well, if you look at the equation up here, right, the 3 meters squared is down in the bottom, and so if I had the electric field at 6 meters along the y-hat direction, then how would that change things? So what I would have is 9 times 10 to the 9 newton per meter squared, newton meter squared per coulomb squared, times 1 coulomb divided by now 6 meters squared in the y-hat direction. And so this would be, instead of 9 divided by 9 to give 10 to the 9, it's 9 divided by 36. So this would be 1/4 times 10 to the 9 newtons per coulomb y-hat. And in fact, everywhere that I everywhere I evaluated that, it along that 6 meter circle, it gives me 1/4 of the magnitude. So if I have, let's do a dash line here. I have a 3 meter circle there, and I expand that to a 6 meter circle. The only difference is all the directions are still exactly the same, but the difference is along this 6 meter circle, I have, I'm trying to draw it, but it's not working very well, exactly 1/4 the strength of the electric field. So the electric field falls off as 1/r squared as it goes away from the thing. And if I went to the 9 meter, I'd find it was even 1/4 smaller than that. Sorry, I guess that would be 12, right? If I doubled the 6, that would go to 12. That would be smaller. In here, right near, it's huge. It's a big electric field. I'm not even going to draw that because that would be too confusing. But you get the idea. Electric field falls off as 1/r squared. The electric field from a positive charge points radially outward. The electric field from a negative charge points radially inward. These are drawn as two-dimensional examples, but obviously they're three-dimensional, right? So it's a spherical outward electric field that comes from isolated positive charges, and it's a spherical inward pattern that comes from isolated negative charges. Okay, so we'll talk a little bit about how you do combined electric fields for certain charge distributions, and then what if you have a continuous charge distribution? How do you compute an electric field from that as well? And so that'll use a little bit of calculus. But this video basically covers the sections 5.4 on electric field and essentially 5.6 on electric field lines, but we skipped over 5.5 where we're calculating charge distribution. So I'll do a little video on that, and that should round out chapter 5, and then we'll move on into Gauss's law.